Hello and welcome to the sixth lesson in Area of Study 2 of Unit 3. Today we will be using all of our knowledge from the previous 5 lessons, and we will be combining that and putting that into an evaluation of an experiment. So without further ado, here is the lesson on lab work in Area of Study 2. So what are we going to do today? We are going to take a look at some of the generic things, but with a focus on Area of Study 2. So what is that going to look like? That's going to look something along the lines of coming up with a testable hypothesis. We're going to consider how we're going to collect data, we're then going to process that data and then report on it somehow. We will then take a look at the very end at some conventions in reporting. So let's get started. We need an experiment, and yes, you do need an experiment. I mean, there's not much else to add to that. These ideas are simply there for you to consider if you have no idea how you're going to come up with an experiment, if you have to come up with one yourself. Now, it's quite possible that you don't need to come up with one yourself and you're given one, or the whole class is given one to do as a group or in small groups. So if you do have to come up with your own, here are some ideas in order to kind of figure out how you're going to go about doing that. For our lesson today, we're going to be taking a look at an experiment that tests the theory that the greater the step-up ratio in a transmission line, the lower the power loss and greater the efficiency. So that's kind of what our experiment is based on. And with that, we can come up with a hypothesis. So a few key things about hypotheses. You need to come up with one that has, or that contains the word that. It doesn't have to exactly begin with the word that, but it has to say something along the lines of, we predict that ... So you've got to take into consideration that when you're writing it, it's not just a statement, it's a prediction. Take into account any mathematical reasoning that might be behind it. Having some idea of the proof as to why it should be the case is very, very valuable, and not only helps when you're evaluating your experiment, but also when you're processing your data. Lastly, and perhaps most importantly, keep it simple. A simple hypothesis is one that is concise and that is accurate and specific, and that really does help when it comes to analysing and testing your hypothesis. In our experiment, well, there's a lot of different ways that we could construct our hypothesis. The best one, in my view, is as follows. So we hypothesize that the number, or that as the turns ratio doubles, power loss will reduce by a factor of 4, which will lead to an inverted truncus of efficiency with an asymptote approaching 100%. And all of that follows. I'm not going to show you the maths behind it, but that's what comes about when you're looking at the power loss formula, the voltage drop formula, and the efficiency formula. So that's what I'm going to predict on behalf of you, and that's what we're going to work with. So with our data, and with your data as well, it's really important to have a solid system, and a really good system is one that uses as much automation as possible. So for instance, linear graphical analysis, you can collect data automatically, you can use the sensors provided with that software and hardware, and that will spit out some really, really easy to use numbers, or not numbers, the numbers might be tricky to use, but it'll be formatted in a way that makes it easy to use. That's really, really important that you have some level of automation, otherwise your practice is going to take a very, very long time to actually execute and collect the data. When you are collecting your data, you should really make sure to look out for anything that may influence kind of your results. So you'd be looking out for, I don't know, perhaps in one specific trial, you made a mistake, you connected the wrong thing in the wrong place, and so your data was off. Keeping track of those anomalies adds to the robustness of your report at the end, or whatever you do, whether it's a poster or a report. If you have the opportunity to use something professional like Excel, Google Sheets is okay. Numbers, if you're on an Apple device, is absolutely garbage, if you ask me. So the strong recommendation is to use Excel, or if that isn't available, use Google Sheets. The reason that I've given that specific recommendation is because that's what's used at a professional level. You don't use Google Sheets very much because its functionality at the moment isn't quite up to scratch in terms of processing and evaluating data. With Excel, there's a huge amount that we can do, well beyond the scope of VCE physics, but it really does assist you if you choose to have any kind of experience, whether it's within physics or even outside of physics. Having skills in Excel are invaluable. So the way that our experiment works, this is kind of the method behind it. We have some mock transmission lines. You may have something like it at your school or whatever. It's a setup that has a couple of lines, literally lines of either copper wire or something similar, and it has a resistor on it to simulate the resistance of a wire. That wire is connected to transformers on each end, and in ours we have a lot of different ways that we can step up and down. So the choices are 0, 8, 12, or 16. Don't ask me why those are specifically the cases. That's just what I had to work with. We are going to record the data by taking a photo of some multimeters. So multimeters are meters that can detect voltage, current, resistance, power, all of those things in one neat little instrument. So that's very, very handy if you have one of those. So if we use a few of those, we can detect the voltage in, the voltage out, the current and the resistance, and that will be able to tell us all the things that we need to know. The data set that I will show you in a moment is actually, it's not exactly, but it's a manipulation of the data that I collected as part of an actual experiment when I was in year 12. So you can be rest assured that this was, I suppose, done in a way that you would be able to quite easily replicate. So let's take a look now at the Excel file that I have, I guess, mucked around with a little bit. And what we're going to look at is testing that theory of step up and step down transformers. So we're going to see how the voltage, power, current, etc., resistance acts in an experimental setting, and then see whether we can support or refute our hypothesis. So this is the data. We have maybe something that looks a little bit complicated, so I'll just take you through what everything means, and then we'll go into the analysis, bit of formula work, and then interpreting our results. So what we have over here is I guess the title of what we're doing. So we're stepping it up by 0, stepping it down by 0. In other words, there's no actual change. Here we're stepping it up by 8 times and stepping it down by 8 times, and then 12 to 12, 16 to 16. So essentially what we're doing is we've got 4 different experiments, if you want to call it like that. And that in each of those we're stepping up the voltage by a different amount, and then obviously stepping it down at the very end after transformation of electricity. So that's the idea behind that. In each of those we take 6 trials, labeled 1 to 6, like so. And in our photos, we take a look at the input voltage. So that's measured by 1 voltmeter, an output voltage before it's being stepped down. So this is obviously between the transmission lines. not before the transformers. So one's before, one's after the resistor. So we've got before and after going, or the other way around. So after being stepped up, before being stepped down. In other words, before the resistor and after the resistor respectively. We've got the resistance of the line, which is measured as per a device that measures resistance, or one of those multimeters. And with that, we can calculate a few things. And that's really quite useful. So we can calculate the current using V equals to IR. So we rearrange our equation here. We go, well, our input voltage divided by the resistance, that gives us current. So in this case, we get 0.2, and then we have an output current afterwards as well. So that's that. We take the power in, so we multiply the input current by the input voltage and the power out, which is the output voltage multiplied by the output current. And then the efficiency is simply the ratio of the powers. Now, there was an issue in this track, and I've deliberately included this issue because I think it's important that we have a look at it. Our assumption of efficiency is that it's power in over power out, which is fine, nothing wrong with that. The problem lies in the assumption of current, because as you know, in power loss, in the power loss equation, we don't actually have the formula, or we assume that current doesn't change, only voltage. So there's a bit of a flaw here, and that flaw is that we assume that resistance is constant, and we assume that both voltage and or current can be derived from the two lots of voltage. In actual fact, it's while this is correct in terms of the scenario, in physics we assume that current's the same. So there is an issue here, something that I would recommend that you explore with your teacher, or contact me, and we can go through the ins and outs of why this was an issue. Nevertheless, we have some formulas. We're going to drag all of these down. So we can copy the formulas, and what we get here is a pretty terrible efficiency, really, based on our measure of efficiency here, power in versus power out. And it's garbage, really. You're losing, apparently, a huge amount of power, and it's just not very efficient all up. That's mostly because we've got a 0-to-0 ratio. We're not stepping it up, we're not stepping it down. So we're essentially not changing anything. And while I'm at it, I can see there's a typo here. There's actually a typo in a few places. Look at that, unbelievable. Whether you notice that as well is a different question. There we go. A bit more Excel skills there. Copying and pasting, not really. So we move on to 8. So we're stepping up by 8, we're then stepping down by 8. And lo and behold, as soon as we do that, we get much better results. You can see here that our input voltage and output voltage is much better. And as a result, we have a much higher efficiency, closer to 95% or so, roughly. And we keep going along and we see, all right, 12 is a bit better. 98% in that particular instance, and when we drag it down, it's about 97. And we do the same here for 16. And lo and behold, we get actually quite a bit of a variation here. So if we look at the average, which is going to be down here, 97.82. Look over here, it's only very slightly higher. So 97.68 versus 97.82. So the way that we've done this, and if I were to put this in here, so this is the turns ratio, so 0, 8, 12, and 16, and we take the efficiency as the average of this. We're going to do the average of that. We're going to do the average of this. We're going to do the average of this. And finally, we're going to do the average of our last thing over here. So as you can see, we have an interesting, I guess, selection of results. And if we were to, I guess, graph that and then pop in a efficiency. There we go. And I'm going to get rid of the borders because that's pretty irritating, and maybe put a bottom border there. So that gives us a little bit of an indication. If we were to plot that, which we're about to do now, then we will find some interesting data. So I'm going to choose a line chart here, or alternatively, I can choose a scatter plot. And I am actually going to use a scatter plot because I feel like that is the most useful. What I'm going to do with that, I'm going to add in everything that I think is necessary. So I'm going to require a trend line. We'll worry about the trend line in a moment. Titles, axis titles are very important. That tells you what each of the axes represents. And on the x-axis, we have the turns ratio. The title would be something along the lines of turns ratio plotted against efficiency. So that's the idea behind that. Now, when we want to put in a trend line, things start to get a little bit complicated. So we could put a linear in. We could. That's fine. But it's not really representative of our data, or in fact, what we hypothesize it to be. So we're going to put in a polynomial. We can't actually put in to the power of -2, unfortunately. So we're actually going to have to try something like a logarithmic graph. And lo and behold, we get more errors. So what it says is that we kind of zero or negative values. Not too sure why that's happening because we don't have 0 or negative values. But it's probably to do with the fact that x is 0. That's I guess the 0 value. It's not going to be able to translate it forward or back. So there's an issue there in that. So what are we going to do? We could attempt to put another version of these, or we can try something else. And what we're going to do is try and raise to the power of -2. So what we're saying is that y is equal to x to the power of -2. So we've said it, we think it's going to be a truncus. So what we're going to do is actually kind of swap that around a bit. We're going to put everything to the power of -2. So this one, the power of -2, and we get some interesting results. And if you were to plot these, which is exactly what we're going to do, we get a very different looking graph in some ways. And that's quite useful. What we've said is our equation should look something like this, or 1 on x squared is the other option. That means that when we alter our efficiency so that it takes this into account, we're doing 1 on x squared there. What we're saying is that this line should be linear. Quite clearly we see it's not. It doesn't take much to consider that. So what we're going to do is display an equation, display an r squared, which tells us the correlation, or it's actually the coefficient of determination, how well things are related. And it's actually not too bad. It looks awful, I'll be 100% honest. But the coefficient of determination indicates that there is a strong link between the x and y variables, which is good. That's what we want. We wanted a strong link to exist. However, in saying that, we still have a little bit of an issue. And that issue comes from the fact that this trend line, first of all, shouldn't be going below 0, because anything to the power of -2 shouldn't be going below 0. But that aside, there isn't really enough data points. And that's a big problem with this particular experiment itself. And there's actually nothing we can do about that. I mean, we could go collect more data, but within the scope of this experiment, we haven't. So that's another thing that you want to always consider is, well, if even though I am plotting a trend line, is it going to be representative because I don't have like enough data? So that's what I really wanted to go through with you, is the idea of processing some data, considering how your relationship is going to be, and then plotting it like we've seen over here with some idea of what's going on hypothetically. So that's it for the data side of things. So what we're going to do now is move back to the presentation, finish that off, and that will do. And with that, we've looked at our data. We've figured out something interesting, that we do have a relationship. Our data wasn't actually particularly conclusive. We didn't have enough of it to give us something useful, and we found that there was a relationship that had a decent correlation, but the data was so varied, and from that we can probably tell that in our very first trial we had some issues potentially. When you get an efficiency of 6%, there's probably an issue somewhere. Notwithstanding the issues surrounding the actual formulas, which I encourage you to look into in your own time and figure out what may have gone wrong there and whether you can potentially improve on it, we can still write some report. We can still draw a conclusion. So we'll skip over that and we'll go over these in a moment. But in our report, what we're going to say is that we did have some evidence that increasing the turns ratio did in fact result in an increased efficiency, whether it was asymptotic towards 100%, probably, whether it was a truncus, probably not. We can't really tell that so easily because we didn't have a fantastic line, to be honest. And that's kind of the core of our analysis. With that, we'll quickly go over the conventions when you're reporting. So what you want to be doing is having a consistent layout with the headings that you need. Obviously, you don't need all of these. This is an exhaustive list. You don't need all of them to write a pretty solid report. Make sure that you're just consistent with formatting, and language should be formal and precise. Your headings should be pretty obvious. That really helps when you're reading a report, when you're assessing it. Citing or using a bibliography is also very good, especially if you've got marks allocated to that. I would encourage you to do it regardless. And obviously, everything you want to be referenced in some way. So that's why you've got a bibliography. And then finally, you've got appendices if you need them, should be in letter order. So those are the things that I think of when I'm writing a report. Not that I write that many reports these days, but when I do write one, these are things that I would often include, or include at least some of these, or take note of them. I would again encourage you to speak to your teacher, see what one of those they want or require, and just make sure you address the criteria that's given. With that, what we've done this lesson, we've gone over creating an experiment, collecting, processing data, reporting it, some conventions, I suppose, and obviously a pretty robust discussion, I hope, on collecting data, analysing it, figuring out what problems you may or may not have. In this instance, we've found that perhaps we need to go back and do some more research, perhaps revisit some of our formulas that we may or may not have used correctly. And that really is the essence of physics. It is experiments, trial and error, and it's a process. And hopefully through it, you learn something that is useful. So that's all for today's lesson. Thank you very much for your attention. Hopefully you found the lesson to be at least interesting. You learned something new, perhaps that you found that it was quite useful for your analysis, because you'll probably have to do some sort of analysis as part of area of study 2. If you want to get in touch, you are more than welcome to head to airlearners.com, and you can find me on the tutors page. Next lesson will be taking a solid run through, I suppose, of a review of area of study 2. Otherwise, that's all from me. I'll see you next time.